A capacitor. A capacitor is a device that stores charges or electricity. There are different types of capacitor actually, but they basically do the same thing. They store charges. You see, the simplest form of a capacitor consists of two parallel plates separated by an insulating material. You just have two parallel plates, maybe a plate here, another plate here, and then with an insulating material in between. This is insulating material. The insulating material is often called the dielectric. So that is that about a capacitor. Most often too, the capacitor takes the name of the insulating material or the dielectrics. If it's made of mica, you say this is a mica capacitor. If it's made of paper, you say this is a paper capacitor. Let's look at the capacitance of a capacitor. That's the ability of a capacitor to store charges. Or you define it, capacity of a capacitor, to be defined as the ratio of the charge on the parallel plates or conductors to the potential difference between them. And we can see capacity of a capacitor represented with C is giving us the charge over the potential difference between the two plates. The capacity of a capacitor is measured in farads. It's measured in farads, the unit of capacitance of a capacitor. So again, we have another formula for capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. Firstly, we have it from our electrostatics that relative permittivity of a material is given as permittivity of the material over permittivity of free space. And then we can have it that if you cross multiply, that permittivity of a material is relative permittivity times permittivity of free space. Now again, same under electrostatics from Gauss law, we are told that electric field intensity is given as charge density over permittivity of a material. But you see, charge density is charge over area. And again, we're giving this to be relative permittivity and permittivity of free space. So that will simply tell us that this is equal to charge over area, then E, not ER, all we have here. Again, also, we have it that electric field intensity is volt over distance. That is to say, electric field potential over distance is electric field intensity. We gave this relationship under electrostatics. We can use that here to say, hence, that V over D, which is your E, is also equal to Q over A, E naught, ER. Now let's cross multiply this now. If we do that, we would have that V, A, E naught, ER is equal to Q over D. Now let's divide both sides by VD, dividing here by VD. If that happens, V will eliminate V here and D eliminates D here. So we are going to have we would have U naught ER A over D to be equal to Q over V. But remember now that the capacitance of a capacitor is given as Q over V. We can equate that with this. Hence, capacitance, which is Q over V, is equal to E naught ER A over D. This is the capacitance for a parallel plate capacitor. So we're given that the ER or epsilon R is the relative permittivity or dielectric constant. Why epsilon? This is actually a Greek letter for epsilon. So epsilon naught is the permittivity of free space. They are all measured, permittivity is measured in farad per meter actually, but I didn't note that here. D is the distance between the plates. Q is the charge in coulomb. So Q is the charge in coulomb. And then A is the area in meters squared. V is the potential difference in volts, and E is the electric field intensity. So I'm noting everything we've used to derive this. Let's take our first question now. A capacitor of charge 5 times 10 to the minus 4 coulomb has a potential difference of 100 volts. What's the capacitance of the capacitor? Well, firstly, what are we given here? We're given the charge 5 times 10 raised to the power minus 4 coulomb. And we're given the potential V 100 volts. So we're looking for the capacitance. C is Q over V, which is Q is 5 times 10 raised to the power minus 4 all over 100. This will be 5 times 10 raised to the power minus 6 farad. You can say 5 microfarad. Micro here is 10 raised to the power minus 6. Example 2, calculate the potential difference across a capacitor of capacitance 2 microfarad if it stores charges of 30 microcoulomb. So what are we given here? We are given the capacitance to be 2 microfarad. That is 2 times 10 raised to the power minus 6 farad. Again, we are given the charge Q, which is 30 times 10 raised to the power minus 6 coulomb. Now we have to get the potential difference. We know that C is Q over V. And hence, if you bring your V and bring your C, you get that V is equal to Q over C. So our Q is 30 times 10 raised to the power minus 6 all over C, which is 2 times 10 raised to the power minus 6. This will give me 15 volts. Example 3. Calculate the capacitance of a pair of parallel plates of area. So we are given now, we are solving. So what are we given? We are given the area, 25 centimeters square. You have to convert to meters square, so divide by 100 square. You know, if I convert centimeter to meter, you divide by 100. So you're converting centimeter square to meter square, you divide by 100 square. If you're converting centimeter cube to meter cube, divide by 100 cube. So this is what we'll have, and that will be 0.0025 meter square. Again, we are given, if you are separated by a perspex of 0.1 millimeter thick, if that's the thickness of the perspex, the dielectric material, that's also the distance between the two parallel plates. So distance is given as 0.1 millimeter. So we simply convert to meter, divided by 1000. This will be 0.0001 meters. Again, we are told that the permittivity of the material, the relative permittivity of the material, is given as 3.5, and that permittivity of free space, E naught, is given as 8.85 times 10 raised to the power minus 12. So we can say capacitance of a capacitor, which is given as E naught ER A over D. Our E naught, 8.85 times 10 raised to the power minus 12 times ER, relative permittivity 3.5, times the area 0.0025, now divided by the distance 0.0001. So this will give us 7 points. So C is 7.74 times 10 raised to power minus 10 farad. So this will give us C is equal to 7.74 times 10 raised to the power minus 10 farad. So take note that the capacitance of a capacitor depends on the following factors: the area of the plate, the distance between the plates, and the permittivity of the medium. You see, the capacitance of a capacitor is directly proportional to the area of the plate, and it's inversely proportional to the distance between the two plates. And then it's directly proportional to the medium, the permittivity of the medium between the plates. Energy stored by a capacitor. The energy stored by a capacitor is given by the relation W is equal to half CV squared, where C is the capacitance of the capacitor and V is the voltage of the capacitor, or the potential difference. Now, we already know the capacitance of the capacitor also is given as Q over V. I could call this equation 1. Therefore, imputing that for C here, we get that W will be equal to half Q over V times, I'm replacing this C with Q over V times V squared. V eliminates one of the V's here, so W is given as half QV. This is another relationship for capacitance of a capacitor. Again, from the above relationship, we can say V itself also, V is equal to Q over C. If we do that, we have that the energy stored in the capacitor can be given as half. I'm putting that into this equation here. Half times Q times, in place of V now, we have Q over C. And this will give us half, Q times Q give us Q squared over C. And so this is another relationship. So we have three relationships: half CV squared, half QV, and half Q squared over C. Example 1. Determine the energy stored in a 10 microfarad capacitor when charged to a 2000 volts. What are we given here? We are given our capacitance, the capacitance of the capacitor, to be 10 times 10 raised to the power minus 6 farad. Again, we are given the voltage here to be 2000 volts. So we can say the energy stored W is equal to 1 over 2 CV squared. That's 1 over 2 times. The C is 10 times 10 raised to the power minus 6 times 2000. This will be 0.01 joules. Example 2. A capacitor is charged with a 10 millicoulomb charge. If the energy stored is 1.2 joules, find A, the voltage, B, the capacitance. So what are we given here? We are given the charge, 10 millicoulomb, that is 10 times 10 raised to the power minus 3 coulomb. And then we are given the energy, 1.2 joules. Next, we want to get what our voltage would be. To do this now, we are looking for V. We can easily say that W is equal to half QV. If you make V sort of formula, you get that V is equal to 2W over Q. That is 2 times, the W is given as 1.2 divided by the charge, which is 10 times 10 raised to the power minus 3. So this will be given as 240 volts. The B now, the capacitance. Again, we know that W can also be 1 over 2 Q squared over C. Now, looking for capacitance, that's the C. If we do that here, we would have that C is equal to, make C sort of formula, we have that C is equal to 1 over 2 Q squared over W, which will give us 1 over 2 times, we have our Q given the question, which is 10 times 10 raised to the power minus 3 squared over W, which is given as 1.2. Here we have 4.17 times 10 raised to the power minus 5 farad, or 41.7 microfarad. Example 3. A 160 microfarad capacitor is charged to a PD of 200 volts. It is then connected across a discharge tube which conduct until the potential difference across it falls to 100 volts. How much energy is dissipated in the tube? Let's solve this question now. The first thing we have here is the capacitance of the capacitor, C, which is equal to 160 microfarad capacitor. Now, the initial voltage it has, I call it V0, is 200 volts. And the final voltage after it has been connected to a discharge tube is 100 volts. The first thing we want to do here is to calculate the energy. Initial energy it has. That will be half CV0 square. So this is giving us 1 over 2. The C is 160 times 10 raised to the power minus 6, then times the V square, which is 200 square. This will give us 3.2 joules. Now we have our final energy, which is W. Again, half CV1 square. That's the final energy it has when connected to the discharge tube, and that will be 1 over 2 times 160 times 10 raised to the power minus 6 times the voltage 100 square. This will give us 0.8 joules. Now we can now say energy dissipated will be equal to initial energy minus final energy. The initial energy is giving us 3.2 minus the final energy 0.8. So this will give us 2.4 joules.